We'll get started. Good afternoon, everybody, and welcome. My name is John Handler. I'm a solutions architect with AWS, and I will be talking to you about log analytics on Amazon Elasticsearch service, and also I'll be joined by Kuldeep Chalan, who is at Expedia and runs a number of different log analytics solutions at Expedia. So we'll have a little bit of an overview, and then Kuldeep will take us into a deep dive, talk about log analytics at Expedia and how that works. Oh, my slide switch. So I want to start the conversation. First of all, who completely new to Elasticsearch? Few folks. Okay. Elasticsearch, obviously very popular technology. Even for folks that are familiar with Elasticsearch, you may or may not know Elasticsearch itself is classified as a database. And I wanted to start the conversation by thinking a little bit about databases and zooming in on Elasticsearch from that angle. So, within AWS, we have a number of different database services. We have relational databases, we have NoSQL databases or non-relational databases, and then we have this odd bucket, which is analytics, where Elasticsearch service and Elasticsearch sits in that analytics bucket. And so when we think about it, and when you think about a database solution, right, every database is designed for a particular thing. If it's a relational database, it is, my slides are not following me the way I want them to. There we go. They're all built with a different purpose, right? So a relational database built with a particular thing in mind, Elasticsearch built with a particular thing in mind. As you think about it, though, you want to pick the right tool for what you're building and for what you're doing, right? So if I am going down to the market to pick up eggs, I'm not going to use my big earth mover, right? That's not an appropriate tool for me to do that. If I want to take a ton of goods across the country, I'm not going to use my pickup truck probably. I'll use an 18-wheeler. So not to stress the point too much, but just we build things and we create tools that have a purpose for which they're intended. Somehow it's going backwards. There we go. And when we look at the databases world, relational databases built to have referential integrity, built to be ACID compliant, all of these things. A key value store focus on rapid and high volume input, ingest, and getting that data in. We have these document and time series databases. These, again, have a focus on the real-time aspect or the throughput aspect, but they additionally provide you the ability to do projections and analytics and other munging of the data that you have. And graph database is sort of a special purpose. So with all of that, and by way of introduction, I didn't do that. I'm fighting with my... Is somebody else clicking? Oh, gosh. That's going to be fun. Yes, please.
I can deactivate the clicker.
Oh yeah, I can just use my. Gosh, this is the old-fashioned technology, right? Yes, I got it. Thank you very much. Okay. Hopefully that's going to stay. All right, so the point of the conversation to this point is that let's think about what is Elasticsearch, what is its purpose? It lives in the database world, which means it's going to hold data and it's going to afford you certain capabilities in terms of what you can do, right? So there are a number of different purposes that Elasticsearch supports. First of those is text search. Elasticsearch is a search engine, much like what you interact with every day, things like Google for web or Amazon for products. A text search engine is good at handling natural language. It's good at scoring and retrieving results that are relevant to a particular purpose, right? And it does that in a way that supports getting the information you need. So that's text search, and Elasticsearch is good at that. Second thing is streaming data. So much like the NoSQL or document databases, Elasticsearch functions to allow you to stream data in quickly and then analyze and visualize the data that is coming into Elasticsearch. And then finally, there's that analysis piece where if I have a set of data, I can actually project graphs from it. I can see what's going on with underlying hardware or other logs that I'm pulling in. Nope, that's not going to work. OK. With AWS, with our Amazon Elasticsearch service, what we're providing you is a native Elasticsearch. And we make it easy to own and operate that Elasticsearch cluster in the AWS cloud. And we'll get into more detail about this. But we came out with this in 2015. Elasticsearch, hugely popular technology. We wanted to bring a service that would bring the AWS kind of goodness of management and monitoring and all of that stuff. So again, just staying sort of in the database scenario or way of thinking, we can look here at an Apache Web Log. And a log line itself, each log line constitutes some kind of event that happened. In Apache Web Log, somebody came to your server, they did a GET request against a particular URL, and then that constitutes an event. With a search engine, every entity is a document. So each log line then is a document for Elasticsearch. And the key kind of idea is that that log line itself contains some structured information. It's not actually structured as a string, but it is information that you can put structure to. So in this case, we have a number of different fields. A field here is something like the IP address, it's the HTTP verb, it's the URL that you went to, it's the response code. All of those things constitute pieces of information that are present in all of those log lines. And as you ingest them, they serve as the basis for what you're going to do with them, whether it's search or analyze or visualize. Elasticsearch works with JSON. So as I start with that Apache Web Log line, I have to go and structure that as JSON. I make field names, things like the verb and the request URL and the host and all of that. Take a piece of JSON and push that to Elasticsearch as a document. Underneath the covers, Elasticsearch works with a technology called Apache Lucene. Lucene is a Java library that provides the ability to read and write indexes. Okay? So the core capability of Elasticsearch is to index data and then provide you the ability to retrieve it and provide you the ability to analyze and visualize it. Under the covers, Lucene is creating indexes on each of those fields. So we've created fields for the verb, we've created fields for the request URL. We pass those off to Lucene. Elasticsearch passes those to Lucene. Lucene takes the values in all of the fields and creates what's called a lexicon. For each value, there's an entry in the lexicon that points back to the document that contained that value, right? So we take all those values and we say, OK, the verb get is present in documents 1, 4, 8, 12, et cetera. This is called an inverted index. And how that supports querying, we'll get to in a second. So all of those field indices are in Lucene, and they're organized into a higher level index, which is the name you use to refer to that corpus of data, that collection of data. You take each of that entire corpus and you split it into what are called shards. Right? So this is for your horizontal replication. You have primary shards that contain the entire copy of the data. Right? So if I have 5 shards, then each shard contains 1/5 of all of the documents that I've sent. And then I can have replica shards that allow me to scale and provide additional redundancy. Again, all of those are organized into a high-level index, which when I send queries, I query at the high-level index. Elasticsearch is called Elastic because it's able to take those shards and distribute them onto a cluster of instances. Those shards, again, represent the data. They allow for querying, and they're the workhorses of Elasticsearch. And what Elasticsearch does is you tell it, OK, I want 5 shards. Elasticsearch says, OK, I'll take those shards. I'll put primaries and replicas onto instances. And then I'll do that in such a way that primary and replica sit on different instances to provide redundancy. And that's how you get the compute and search from Elasticsearch. So if we think about how to scale Elasticsearch and how Elasticsearch scales, the first layer, the easiest thing to think about, is Elasticsearch is a storage medium. I'm sending my documents in, it's creating indexes, and those indexes are written to disk. On disk, an index is not the same size as the original source data, right? Because I'm cutting it up and putting it into indexes, that's a different data structure. But actually, it's pretty close. Usually, we see about 10% inflation source to index size. There are various parameters that you can tweak to change that ratio, but 10% larger, that's a good place to guess. Every time you add a replica, then you increase your storage need by 1x. So if I have a primary and a replica, I need 2 times the storage for that index. So when I'm thinking about initial scale and initial deployment, what I do is I pick a number of instances that supports the amount of storage that I need for my indexes. For example, if I have a 1 terabyte corpus, right, with inflation, I'll have 1.1 terabytes of index. I'll want a replica, so that means I need 2.2 terabytes of storage. I can deploy 2 instances, each with 1.5 terabytes of EBS to get a total of 3, and that is where I can start. So shards themselves are actually both units of storage and units of compute. Again, this is how Elasticsearch distributes the data. It's how it responds to your queries. So some people don't get the monkeys. The monkeys are the shards. So we can look at, now you set the shard count, right, when you create an index. So you tell Elasticsearch how many primary shards you want to have for your index. And everybody should do that. There's a default of 5, which is frequently not right. What we like to say is that you want to target 40 gigabytes per primary shard. Okay? So going to my example, if I have a 2 terabyte corpus, I would think 50 primary shards would be the right number of shards. Okay? For i3 instances with NVMe SSDs, high disk bandwidth, high network bandwidth, in fact, we say you could go as high as 100 for those, targeting 90 to give yourself some overhead, right? You always want to use at least 1 replica in production. So your replica, your first replica, again, provides that data redundancy. So you set it up, you say, yeah, I want 1 replica. Additional replicas you use to increase your query capacity. But that first replica is very important. If you're running multiple different indexes, multiple different tenants in a cluster, it's important to try to keep the shard sizes roughly the same. And that's because Elasticsearch actually distributes the shards to instances in the cluster based on a count of how many shards are on each instance. So if they're radically different sizes, you can actually get hotspots for storage. So you set up your sharding, you set up your instances, and then you have to get data into it. So this is an area that Kuldeep will be spending quite a bit of time on. So I'm just going to give you a little bit of a conceptual framework to understand what's happening in terms of ingest. We'll take questions or come see me afterwards. Thank you. So your ingest pipeline needs to accomplish several tasks. The first thing it needs, you have some data sources, right? So this is your servers, this is your applications, this is maybe S3, this is maybe your containers. There are a number of data sources. You need something on each of those data sources or that connects to each of those data sources that can ship logs off them. There are a number of different technologies here, some of them open source, some of them AWS, that make it easy to collect those logs. After you collect the logs, then they're going to be strings. You need to transform them into JSON. Again, there's a number of technologies here. One open source technology is called Logstash. If you're using Kinesis Firehose, it's a great solution. Kinesis Firehose can do this transformation inline as you're sending data across. CloudWatch Logs can also do this transformation within AWS. You also want to buffer these JSON documents. You can connect and send one document at a time, but the overhead of all of those connections will quickly swamp your cluster. So you need to create bulk batches that you're going to send off to Elasticsearch. Again, a number of different technologies. Each of them some of them can do this in various ways. And then finally, you need something to deliver to Elasticsearch. Something has to actually make that request to the Elasticsearch cluster and send the data in. We'll see 3 really good examples from Kuldeep, and there's many ways to do this. But that's the framework that you use. No, that's still not working. OK. When you send your data into Elasticsearch, as we said, there's the individual field level indices, but actually there's a larger logical collection of those, which are the big top level indices. For streaming data and log analytics, the pattern you use is index per time period. This is supported by most of the ingest technologies directly, or there are APIs within Elasticsearch that would let you accomplish this rolling index structure. Thank you. Now there's like a bunch of buttons, and I don't know which one is what. I'll figure it out. So normal structure is to create an index per time period, and the usual time period is to create an index per day. Again, this is supported by a number of the different ingest technologies, right? We see at about 1 or more terabytes a day, maybe 2 terabytes a day of ingest, you start to get into need for an hourly index structure. At less than 250 gigabytes, maybe you go to weekly index structuring, but most of the time it's a daily. And the reason that you do this is it actually makes it easier to manage the data in your cluster. With Elasticsearch, it's very easy. You send an HTTP delete to delete out an old index. And that's the cleanest, easiest way to manage that data. Often you'll take a snapshot or archive that index somewhere before you delete it, but there is a daily rotation where you just delete off the oldest data. That one is not, no. I'm still fighting it. Well, let's just jump here. So we'll talk about the query engine. Within Elasticsearch, you send a query, something like, tell me status 500 on my HTTP requests, right? That goes to some index, or it can go to multiple indexes. And that is distributed across the cluster to some node. Some instance in the cluster gets that request. That's going to act as a coordinator. That coordinator then distributes the query to each of the shards in the indexes that it touches. Could be a primary, could be a replica, but the coordinator sends to one of each so that the whole corpus responds to that query. Each shard then figures out a response to that query, sends it back to the coordinator reaggregates, sends it back as a result. So when we process a query in Elasticsearch, we come back to Lucene and the inverted index, right? So we take a certain set of fields and we say, tell me this field has this value, status 500, size greater than 50,000, whatever it is. We go to the inverted index and we look up the values, right? So if I'm looking for statuses 500, I'll go to the status index and I'll get the posting list, which is all the documents that have status 500. I repeat that for all of the portions of the query, and then I apply the logic of the query to either intersect or union the sets of posting lists to come out with the total posting list, right? So if I said status 500 and request includes Star Wars, so I get status 500 posting list, request Star Wars posting list, it's an and, I do a set intersection, and I get the matches for that query. That's what I return, well, I get the matches for that query. I then go and score each of those matches, mostly, usually, and sort them by how good a match they are. That's what I return as my result. With Elasticsearch, you also have the ability to do more complex statistics on the values that are in your field. So this is fields. This is how Elasticsearch supports analysis, right? I have the same kind of thing. I take my result set, right? I then look at the field data. Let's say I want a histogram of the verbs that came from a particular IP address. So I look up the IP address, I find all the documents, I go and look at the verb for each of those documents, and I can easily create a histogram out of that. The verb itself, the values provide me buckets, things like get, put, post, head, what have you. And then I can just count how many times that happened. Underlying all of this sort of analysis that Elasticsearch does is this mechanism. I can use that then to build visualizations on what's in my log lines, right? So in this case, what I did is I graphed a breakdown of my traffic based on the URL. I graphed a pie chart with all of the requests that are coming in so I can see differentially what are my users interacting with. I have a keyword cloud because it's the 90s still, but keywords are cool. So I have a keyword cloud that shows me what are people searching for, and I also have a response code graph that lets me know these are the 200s, and then the gold bars there are errors. Now, it's a search engine. Like, all of this stuff is in a search engine. So if I want to find the 500s, I can just search for them. If I'm trying to diagnose some problem in production, I can dig in and I can find the individual log lines across all of my servers that generated 500 errors. That's kind of the power of Elasticsearch. That's where we see most people adopting and using it. I'm still going to struggle with this a little bit. So I'll tell you about two different customers, and in some little detail, and then Kuldeep is going to tell you a lot about Expedia. So the first case study is MirrorWeb. I love these guys because not so much for Elasticsearch, but for the way that they got data into Elasticsearch. So they had 120 terabytes of the United Kingdom's web and parliamentary archives that they had to chew through and send into Elasticsearch. The data was not clean, there were duplicates, there was all kinds of stuff. So they deployed about 1,000 Spot instances, broke the data sources into 100 megabyte chunks, and then chewed through it all in about 10 hours to load all of that data. They ended up with an index in the like 8 or 9 terabyte range. But this was just a fantastic use of Spot and EC2 and data ingest at a really extremely high volume. They were 10x the speed of the prior record, which was with Hadoop. So they did a great job with that. So another case study, Financial Times. Financial Times, obviously online media, also paper media. They track their user interaction against their website. They take their web logs, they ingest them internally, and they have a system that they call Lantern that they expose the interaction with the site to the journalists and editors so that journalists can get excited about, like, hey, I published this article and everybody's loving it. And the editors can say, hey, this is a great topic area. We should go and publish more about it. So they did a really nice tool there. All right. I'm going to talk just a tiny bit about Elasticsearch Service and let you know what the service provides and sort of how we provide it. So the number one thing is, with the service, we wanted to provide you the ability to run an Elasticsearch cluster in the AWS cloud where you would get an equivalent experience to what you would get with open source. So we wanted you to be able to use Elasticsearch like you're already using Elasticsearch. We make it easy to use. So Elasticsearch clustered technology, there's a lot of deployment, there's a lot of configuration. We do all that stuff for you. You just send an API call, we deploy a cluster. We make it scalable, so if you're running on a particular set of instances and you want to change that set of instances to a different one, you want to change your storage, anything about add nodes, it's a single API call. We just make it easy to scale it up. We have security built into the service that allows you to secure your cluster from outside intruders. We have a feature to make it more highly available. With a checkbox, you can just deploy to 2 different availability zones. And we have tight integrations with other AWS services. I mentioned Kinesis Firehose, CloudWatch Logs. We have nice tight integrations, IoT as well. When you use the service, again, you use the console, SDK, CLI. You send off that API call, and you tell us how many data nodes you want and how many master nodes you want. We go off, we deploy that, we build it into a cluster, and we provide that to you over an HTTP endpoint, right? So there's a DNS entry RESTful endpoint. We put load balancing in front of the cluster, and then we also use, you use IAM to block that cluster or provide access control. In addition, we send monitoring data to CloudWatch so you can monitor your cluster, figure out how it's performing, do you need to scale it? And we also send administrative usage to CloudTrail. So if you want to know who's building clusters, who's taking them down, et cetera. So we'll talk in a little teeny bit of depth about some of these. So in terms of security, again, we provide you a DNS entry, which is an endpoint. That DNS entry can be publicly available, so it's a public endpoint, or it can be within your VPC. If it's a public endpoint, we recommend that you set an IAM policy that limits what anonymous users can do there because people will find it. And so you use IAM to secure that. And then if it's within your VPC, that DNS resolves to the address space within your VPC. So it's not available outside of the VPC. In that case, you can also use IAM policies to provide granular access control for different actors in your organization. And then finally, we support encryption based on your KMS keys. This is encryption at rest. I briefly touched on dedicated masters. Within Elasticsearch clusters, there is a master instance. That master instance is responsible for orchestrating the cluster. It knows all of the schema, it knows all of the instances, it knows all of the indexes. You need that master function to keep the cluster being a cluster. Now the problem is if you put that on the data node, and you're running like hot with queries and updates, that query node can become loaded and you can't respond for master functions. So what is recommended, and especially for production, is to deploy dedicated instances that do nothing but the master function. And you should use 3 dedicated masters quickly because the master is elected based on the eligible nodes, and 3 doesn't divide evenly if you have a network split. So you should use 3. They can be much smaller than the data nodes. They don't do a ton, they just orchestrate. But they do make your cluster a lot more stable, so in production, those are always recommended. Dev and test, if you can rebuild the cluster in an hour, it doesn't matter so much. I mentioned zone awareness. Zone awareness, again, just a checkbox. With this, we put your instances in your cluster into 2 different availability zones. We split primary and replica shards. You have to have a replica, but we split primary and replica into those 2 zones. That gives you 100% of data in both zones. So should you lose a zone, you retain all that data, and Elasticsearch continues to function. Now, I mentioned we send metrics to CloudWatch. These are some of the important ones that you want to set alarms. First of those, cluster status red. If your cluster is red, it means that you've lost a primary shard somewhere. If we're blocking writes, definitely you want to know that. For the CPU utilization, we like to see the average CPU utilization across the cluster, 80% or below. We don't like that to go above 80%. JVM memory pressure tells you how much data is getting stuck in the old pool in your JVM. If we see that go above 80%, that's a problem. And if it goes linear up and to the right, that's also a problem. So putting a alarm there helps you catch that. Free storage space, we like to see 25% of the total storage remaining free. So you set an alarm at 25%, and then you scale it up. And then we take automated snapshots in the service. If one of those fails, you probably want to know that. OK, so we also, within Elasticsearch, you can set a threshold for Elasticsearch to write a log line if an index takes longer than that threshold or if a query takes longer than that threshold. Within the service, we make it easy for you to set that up, and then we push those slow logs out to CloudWatch logs. This is really useful if you want to figure out, what are my slow queries? What are the things that are not performing in my cluster? You can use slow logs to get a report about that. Within the service of the cost model, we have 3 components. You pay for instance hours for the masters and data instances. You pay for EBS. Within the service, you can choose EBS or the ephemeral storage on the instance itself. If you choose EBS, there's an EBS charge. And then data transfer, standard AWS data transfer applies. All right, so that is a quick overview of the service. And I'll bring up Kuldeep now. Thank you very much.
Thanks, John, for the overview of Elasticsearch, talking about how it is helping folks analyze the machine data out there. So I'm Kuldeep Chauhan. I'm from Expedia Group. Today I'm going to talk about three different things, talk about the usage of Elasticsearch, why did we choose Elasticsearch service that Amazon is offering over the open source one. And I'm going to talk about three different architectures of how folks are using Elasticsearch service within Expedia. For those of you who don't know, Expedia Group is one of the leading travel, online travel industry leaders. We have a lot of brands that make up Expedia Group, like Expedia, HomeAway, Orbitz, Cheap Tickets, What If. I think pretty much apart from Priceline and Booking.com are under Expedia Group. I've been with Expedia Group for the last 5 years. Very recently, I transitioned from brand Expedia to HomeAway brand, and I moved to Austin. I'm a newbie to Austin now. I used to live in Seattle. With that, I'll get started on the usage around how many Elasticsearch clusters are we running. So we have about 175 across different accounts. When I say accounts, I'm not talking about hundreds of accounts, probably like 3 or 4 accounts that we have. And the number of instances that are powering these clusters are about 500. Of all these clusters, really, there are about 5 to 10 clusters that are the heavy hitters. Everything else, folks, either they want to try out Elasticsearch or it's like low amount of data that we pump into these systems. The amount of data across all these big clusters is about 35 terabytes, and I'm only talking about production here, not test or stage. And that too, this is not that we keep this data forever, right? Like, as John mentioned, we do roll over the indexes. So one of our biggest cluster has about 10 terabyte, but we only keep 3 days worth of data in it. We don't keep more than 3 days worth of data. So we pump in a lot of data, but again, this is more used for analysis, not something to use for our historical data or whatnot. A lot of the historical data goes into S3, and from there, if we need to pull the data back in, we pull that back into Elasticsearch. So I think the bigger question, right, like as John mentioned, there is an open source solution. You can spin up your own EC2 instance, go and install Elasticsearch, Logstash, whatever, right? That whole stack that you can install yourself. And we used to do that as well, right? Like before Elasticsearch service came along, we used Chef to install Elasticsearch onto it, create an image out of it. And then when we needed a cluster, we were able to fully automate it. But the bigger problem was, how do we scale it, right? Like when we ran out of the data on the nodes, how do we increase the size of the cluster? Those were some of the challenges with that we didn't spend time on automating. And it was painful as well, to be honest with you. And then Elasticsearch service came along. As John mentioned, it is very easy to set it up, right? Like you go to your console, you can use a CLI. What we do is we use the AWS SDK, and then we wrap it with some automation so that we have governance to make sure that there are enough tags, and then also apply some security policies on it so that it's not wide open to everyone. A lot of folks who have used Elasticsearch might know it was wide open for a long time, a lot of clusters, and people were able to access those clusters from any location they can. So that's what we did, was just wrap the SDK using, and then put some governance on top of it. But creating the cluster was within minutes. We had the cluster. People will go to a Jenkins job and say, I want I2 2 extra large, I2 4 extra large. I want this many number of master nodes. And then 10 to 15 minutes, we have a cluster up and running. That was the biggest selling point, to be honest. And then the second one was the high availability, right? Where and a lot of the times, no one knows what is the amount of data that they are going to pump into the systems, right? Like you will start with maybe 1 terabyte that you think, but for whatever reason, someone changes a small field in the log statement, or there is some additional data, 1 terabyte becomes 10 terabytes. So the high availability feature of Elasticsearch service gives you that option to scale when you want to scale, right? Like if you want to add more number of nodes, or if you want to add more number of like data nodes versus more number of master nodes, what type of instance you want. You can all just do that through a console or SDK, and then within, like again, as I said, based on, it typically takes minutes, but it depends on you, how much data you have in the cluster as well. If you have terabytes worth of data, it may take more time for it to be rescaled versus, but at least you don't have to worry about it. Someone else is doing it for you. And the security is one, I think, as I mentioned earlier, the VPC support that John showed was a recent feature. Sometime end of last year it was released. Before that, it was not there, right? Like, and when you created an Elasticsearch cluster, it was wide open. Again, this is a simplified policy. This is not the real policy that we applied. The point is, you see the bottom, there is an IP address that we use to scope, so that we only give access to someone who is running within Expedia's network, or if they are running inside the inside our own VPCs. Basically, this address would be a NAT IP or your office public IPs. And if you are running in the VPC, you typically used to give full access, but again, we scope it to the IAM roles that need access, full access. So that's how we were able to implement the VPC, scoping the R clusters to VPC before the VPC support came along. And the last one, monitoring and backups, right? Thankfully, we never had to do a restore of a backup yet, but you know that there is a backup feature that you can just enable, and then you at least have that peace of mind that someone is taking the backup. And we haven't done that yet, but we know that it's available if we need to. With that, I'll talk about 3 different architectures today of how we are using Elasticsearch. And my aim was to do more breadth than depth, right? And if you need any details, I'll be happy to talk to you after this session. But again, my focus here is more breadth versus depth. So these are 3 different architectures that I picked to speak today. One was, how do you stream the Docker startup logs into Elasticsearch? Then how do you analyze the data that's there in CloudTrail to solve a business case, right? I'm going to talk about the business case there, why we parts like analyze the data that's available in CloudTrail, and then how we are using Elasticsearch within our distributed tracing system. So these are the 3 things that I'm going to talk today. Docker journey at Expedia started like 3 years back. We are heavy users of ECS, the EC2 container service. We chose it again for the reasons of it was managed by AWS. We can focus on writing the apps and then pushing our stuff into AWS than trying to run clusters ourselves. With that being said, by that time and even today, our log management systems for like the application logs, if you will, are written to a file, and then we use Splunk to visualize all that application logs on a continuous basis, right? Like once the app is running, then it will write to the disk, and then the data will push to Splunk. With Docker, what we did was we used something called a sidecar approach. So we always run a Splunk container as well. The challenge what we ran into was if the app was running, then we could stream the data into Splunk, but sometimes the app wouldn't even start. Then how do you capture those logs to understand why a particular Docker app didn't start up? So that's where we use Elasticsearch service. Splunk did not provide a log driver on Docker at that point. Like Docker 1.7 is when they started enabling this feature called log drivers that you can use to pump data to different sources. Of course, it didn't support everything that was out there. So that was the high-level problem that we were trying to solve here to make sure that the folks understood why their app didn't start. So as I mentioned, we used ECS. ECS are a cluster management solution. So what we did was on both ECS log driver and the Docker itself's log driver, like the task or the container, we pumped both the logs for those two, ECS agent and then Docker, to Fluentd. For those of you who don't know Fluentd, Fluentd is an open source solution which unifies data collection and consumption. So it decouples the data sources from the consumers by just providing an interface where you could have multiple data sources pump the data into Fluentd, and then you could have multiple subscribers of that data as well. And what we did here was there was no Elasticsearch log driver. So that's the reason we set up Fluentd clusters ourselves in AWS, and then we created the Amazon Elasticsearch service clusters, and then configured Fluentd to pump the data there. So very quickly, right? Like it was very easy for us to set it up. Once we had this, we figured out how do we do the Fluentd part. The spinning up the Elasticsearch clusters was pretty easy for us. Then we spent some time figuring out how we do that with the Fluentd part. Once that was available, then people would go to Kibana to do their searches. What we used to do with this is when a particular app didn't start or particular deployment failed, we would send an email, in the Jenkins job itself, you would see a hyperlink that talks about, hey, this is your app name in Kibana that you can go and search for. So as people would just click on it, and then they would be able to see why their particular app didn't even start. So that way, people were able to visualize the errors. Of course, once the app was fully running, the logs used to go to Splunk, and then people can go and take a look at it if there is an exception or whatnot. Very quickly, this is the setup that we did. It was pretty easy to do. We just said anything that comes to Fluentd, we would, this is on the Docker. Anything that we pump to Fluentd, we would tag with the Docker version itself, like whatever was the Docker image tag, we would just tag that particular log that we pump to Elasticsearch as well. And then within Fluentd, we were just blindly, whatever was pumped to Fluentd cluster, because we set Fluentd just as a bridge here to just push the data out to Elasticsearch. So anything that came into Fluentd would go to Elasticsearch, and these were the different Elasticsearch domains that we set up in different regions, in different environments. So each Fluentd cluster had its own configuration, if you will, to send it to the appropriate Elasticsearch. Again, that's how we were able to solve that. Again, we continue to iterate on it. But again, it has been super helpful for our folks to actually visualize some of this stuff, why their apps were not starting up. For those of you who don't know CloudTrail, CloudTrail records all the APIs that you make in your account and then pushes the data into S3. We had an issue with that we were trying to solve here. We are, as I said, we had like 3 or 4 accounts. And most of you who are heavy users of AWS would have run into API rate limiting. If not by now, maybe later on. So we were constantly hit by that API rate limiting issue, that we needed some level of data to understand who was that IAM user or IAM role who was making that many number of calls. And we also wanted to know which service was that making, whether it was load balancers or whether it was ECS or EC2 in general. And we wanted to know it very quickly, right? We didn't have a lot of time to analyze because either we were not able to push our changes to AWS because we were rate limited. So Elasticsearch came in very handy there, where we were able to just spin up the cluster. What we did was on CloudTrail, we created this CloudTrail configuration, if you will. And what we did was create a CloudTrail for all the regions. Earlier on, 3 or 4 years back, you would have to do that for each region at a time. Now CloudTrail provides you an option to just say, hey, I just want to record all the things that are happening across all the accounts, and then send that to an S3 bucket. So on S3, Once the data gets into S3, we had an SNS notification as well configured, so that whenever the file got deposited into S3, we would get an SNS notification. There are a couple of ways how you could invoke a Lambda from here, right? You could invoke a Lambda directly from SNS, or you could just create a subscription on the bucket itself to say whenever a file gets deposited, you could just call a Lambda. The reason why we chose this one was this gives us options to have multiple subscribers on the same SNS. On S3, you scope it to a particular prefix. Then you have to deal with those prefix wars. If someone had a blanket prefix and someone wanted a subset of that prefix, there were some issues with how you can invoke a Lambda from there. So that's the reason we chose SNS here. And then once the data was available, that notification kicked in our Lambda. We just read the data from S3 and then pumped into Elasticsearch service. It was, to be honest, it took a day for us to do all this, not more than a day. It would have been even less than a day. And once data was available there, right, like we were able to create some dashboards to understand the top API callers or whatnot from our account. I'll show you a dashboard in a minute. So that was very quickly that we were able to solve the problem at hand with the help of Elasticsearch. And again, this is some configurations that we did. On the CloudTrail, we said anything that comes in for all the regions, just send it to an S3 bucket. And then we had an SNS to Lambda trigger. And this is all the code that we wrote. Maybe a little bit simplified here for the sake of presentation, but that's all we had to do is just get the data from S3 and then push it to Elasticsearch. And all that Elasticsearch domains and whatnot was all like environment variables on Lambda. So once the data was there in Elasticsearch, this was one of the dashboards that I just talked to understand the API calls, who are making the top API calls, again, for the last 10 minutes. Once the data is available in Elasticsearch, you can slice and dice however you want. This was one of the dashboards that we built. And I have also open sourced this solution as a serverless application, so you can use SAM to run this application fully end-to-end with the CloudTrail configuration. It does create an S3 bucket, create a Elasticsearch domain as well for you, and then does that wiring, which will send the data to Elasticsearch, and then you can create your own dashboards however you want to whatever solutions that you want to create. And the last one that I wanted to talk today was how we are using Elasticsearch within our distributed tracing system. Again, for those of you who are transitioning from big monoliths into a lot of microservices, someday you would need this. I'm sure some people might have already been using it. Again, this is to understand when a request comes to your site, how is it being traversed through across all these microservices that you have. The one that I'm showing here is from Twitter. It's called as Zipkin. Uber did their open source called as Agar. We are working on open sourcing this. We call it as Haystack internally. We use open tracing to collect all this data and then customize it to Expedia's environment, if you will. And then our teams would use it to do their traces. Very quickly, right? Like, again, I don't have something to point. The one in the top, it's typically called as a trace. Trace is a single operation performed by an app. It could be just calling one service, or it could be calling 1,000 more services behind the scenes. And the ones that you see later on are called as spans. The span typically says how much time it took, when did it start, and typically a trace could have multiple spans, and they could be also nested ones. The reason why I'm bringing this up, right, like as we were collecting all this trace information, we were pushing all this data into Cassandra as a key value pair to store all these traces for every app that we were running. But we also needed a way to do easy way to do some kind of query on top of it. And doing queries on top of Cassandra were costly for us. When I say costly, not the money aspect, but the time it used to take. Then trying to put the data around was also something that was time consuming. I'll talk about a few of the use cases that we solved through Elasticsearch once I talk about the architecture. That was what we were trying to solve here. With all of our microservices that were running in AWS, we created a Java library. Most of our stack is Java. So we had a platform library that every app would just add in. And then what that does is it generates a trace for each of that particular request that app is serving, and then pushes that data into Kinesis. So we use Kinesis as a collector, if you will, to collect all the data that was coming from all these different microservices. So we had only one Kinesis stream per environment, and each of that Kinesis stream would pull that data in and then push it to, and what we did was we had a Java app that would read from Kinesis and then send it to Kafka. For folks who who knows Kafka and Kinesis, both of them are similar, right? Like the way that they are trying to solve is almost the same. The reason why we have both here is one, Kinesis is highly managed, highly available, fully scalable, but again, it's also expensive. So what we do there is push all the data to Kinesis, and from Kinesis, we again push it to Kafka, and we have multiple subscribers of that data from Kafka than having those subscribers on top of Kinesis itself. So once the data is in Kafka, then we have another app that will actually get the data from Kafka, do the same thing as what John mentioned. We do batch it. We don't send every record that comes into Kafka into Elasticsearch. So we batch it, and then once the batch is based on some predefined values that we have, if it reaches a certain size, then we push it to Elasticsearch. And also, we also do a time frame as well. It's not just we wait for the size to be a particular size. And then once the data reaches that particular size, we push that into Elasticsearch service. And then we had a Node API, a Node UI that would interact with this Elasticsearch service to get that data. The way that we actually used this data was when we push the data into Elasticsearch, we always annotated the data saying that this is the source, the trace ID. As you can see here, like the transaction ID is what we call it as trace ID, and it could have different multiple metadata, right? A particular trace could have, is it Expedia.com, is it Orbitz.com, like we call it as TPIDs or whatnot. There's a lot of metadata that we store in our systems. The reason why we do that with this Elasticsearch solution was to be able to do queries on top of the data that we have. So example, someone would come to our dashboard and say, give me all the traces for the last 1 hour, right? What we would do is we actually go and first query Elasticsearch for that data. Once we get that information from Elasticsearch, then we use that trace IDs that I just showed you, and then go and make that call to Cassandra to get the actual trace data to show. So that's how we are able to use Elasticsearch. And then the second aspect was, example, just what I said, right? Like the filtering the traces. If someone wanted to know, hey, give me all the traces, but I want to know only trace for this particular app, then we also do that using Elasticsearch to get all the traces for a particular service, and then we send that to, then we pull that from Cassandra and then display it. And again, I'll try to wrap it up quickly. Things to keep in mind, right? Like I've talked so many things about Elasticsearch, how it has benefited. First thing always, when you talk about scaling actually results in a new cluster. It is not resizing your existing cluster. The reason why I bring it up here is when your system is already getting hit by a lot of requests for whatever reason that Elasticsearch is already unhealthy, you typically don't want to do a resize again at that point because one, the JVM pressure is already high, and then you're asking it to again do a resize, which means the data is being copied from your cluster again to a different cluster. So you are going to really hurt your cluster. Sometimes it's maybe better off to not do the resize until your traffic load reduces, and then do the resize. Just keep that in mind. Even though Elasticsearch service does a lot of the heavy lifting, you own the monitoring, you are responsible for your clusters. Like there is no magic wand which will automatically scale or resize. So you have to keep, like, you have all the tools, right? Like I'm not saying the tools are not there. The tools are there, but you actually own that responsibility of monitoring and scaling, whatnot that you have to do. Again, these two are wish list, which I think I brought it up in reInvent as well. With Elasticsearch has been evolving very rapidly, right? Like now I think it's 6 is the version 6.x whatever. If you want to upgrade from one version to a different version, there is no magic button, unfortunately. You have to create a new cluster, take a dump of your existing cluster, and then push it to the new cluster. For most part, it does work. I haven't seen any backward compatibility issues in general. Not backward, like maybe the upgrade issues. But again, I wish there was upgrade button. And then this is, again, just a small detail. This was more for me when I was trying to collect the stats around all the clusters. There was no way to tell me how much we are actually using. It does tell you how much is left on the cluster, but it doesn't tell you how much is actually being in use. And then the last one, just to wrap up, the real benefit for us was the ease of setting it up and the high availability. The rest of the two are essential, right? Like you can't escape from security. You need to make sure that your clusters are protected. So that, and then the last obvious one, the monitoring and backup. With that, that concludes my presentation. If you have any questions, I'll be around to answer. And please make sure to review our talk. Thank you.